That is not a chip problem. It stopped being a chip problem a long time ago. So anyone who's thinking about, let's design one chip and prove it out, they're going to have a rude awakening.
Welcome to AI with Sally, an EE Times podcast that brings you inside my conversations with luminaries of the AI chip industry. This episode is brought to you by our sponsor, Lemurian Labs. Today I'm joined by Lemurian Labs CEO, Jay Dawani. As we scale AI from single servers to massive clusters with thousands of GPUs, the industry's focus at the chip level may be missing a crucial part of the story. Jay argues that the kernel, which is the fundamental building block of AI software optimization for the last 10 years, has basically become the new assembly language. In other words, it's powerful, but it's increasingly inadequate for the complexity of modern AI infrastructure. In this short conversation, Jay explains why the future of AI performance may depend less on faster hardware and more on rethinking compilers, programming models, and system-level optimization, and why he thinks a post-kernel world could reshape everything from AI research to the competitive landscape for AI chips. Here's my conversation with Jay. Okay, very pleased to welcome Jay Dawani to the show. Jay, welcome.
Thanks, Sally. Good to be here.
So we're going to talk about everyone's favorite AI topic, which is compilers, obviously. To set the scene, I think when most people think about AI infrastructure, they think about chips. Or certainly people who listen to this podcast probably think about chips. I think you think that we're focusing on the wrong thing. Like we, the industry, think it's a hardware problem, but you think it's more like a systems and a compiler problem, right?
Partly. I think hardware is still important, right? We still need hardware. It all has to run on something, right? But the problem is more, we don't have chip companies anymore, and we don't need chip companies anymore. We need companies that build large systems, and that's a very different design problem, right? When I started in AI, I could do a lot of things on one GPU, right? And I could still publish something. Today, if I want to be at the frontier and I want to do something interesting, I need at least 20,000, maybe closer to 100,000 to really prove something out. I have seen runs at north of 100,000 GPUs.
Wow.
That is just the world we're in, right? And you're looking at intense scale for just the last 14 years. Right? Nothing has scaled this quickly before. But what does it take? Like, what does it entail going from one GPU to supercomputers or, multi-campus, multi-gigawatt data centers abstracted looking as one machine for one large training run? Right? That is not a chip problem. It stopped being a chip problem a long time ago.
Yeah.
So anyone who's thinking about, let's design one chip and prove it out, they're going to have a rude awakening, right? NVIDIA is winning not because they know how to build a better chip. They build amazing chips. But NVIDIA has been a systems company for longer than people know.
Yeah.
Right? And that involves thinking about the workload, the libraries, the domain-specific language you write in, the compilers, the runtimes, the drivers, the hardware, the packaging, the memory, the networking, and everything else that goes with it. Right? And there's many different topologies that it can exist in. There's many different parts of the market that want different types of things, right? So there's people talking about Ethernet scaling. There's Ultra Ethernet as well, InfiniBand, eventually CXL if that ever happens. Then there's everything around the photonic interconnect world, and that impacts packaging. You have to think about chiplets at modern nodes and all the other things that come with the manufacturability. In order to get performance, and you're thinking about transistor density and memory, that involves thinking about, eventually heterogeneity if you care about energy efficiency and performance. Right? And you have to think about the memory hierarchy. The memory hierarchy is the execution model on a lot of these things. Right? And if you think about what the modern chips look like today, they're basically miniaturized versions of the petascale supercomputers from 20 years ago. Right? So the programming model and execution model have to change in accordance with that. They can't just stay the same. So you have to think about all of this as one co-designed system across every single layer of the stack. And that's what I mean. It's like, it's not just a hardware problem. It is a systems problem. And you have to take everything into consideration because performance and efficiency and scalability all matter. Like there's no other way of realizing this.
So I agree with what you're saying about taking every layer into consideration, but compiler kind of is in the middle, like is absolutely
It is.
critical to all the other layers, right?
It is. Like I think compilers are the world that tie together all the other worlds.
Yeah.
Right? If you think about the importance and where it came from, why do we have compilers in the first place? If you go way, way, way back, like 55 or 60 years ago, we wrote things basically in assembly, right? But chips were super simple then. Like architectures were very, very simple then. So you could do that. But as hardware got more complex, as things got smaller, there was more to keep in your head,
Yeah.
right? And eventually built abstractions on that so that we didn't have to deal with complexity and we could surface the things that were important,
Yeah.
right? So you have to raise the abstraction level. You need a new programming model, and you need to find a way to map the thing that a person wrote onto that hardware while maintaining correctness so you can get performance and things out of it,
Yeah.
right? But hardware was still simple enough that you wanted to have some degree of control over it, right? Every time we have changed hardware, things have gotten faster, they've gotten smaller, they've gotten bigger, they've gotten more complicated. The abstraction level has had to change with it to allow for developer productivity to continue, right? Eventually, we had many different vendors. Every single vendor had a slightly different design. Portability became hard. There was the entire floating point debacle at some point, which is why we started standardizing things, because we cared about correct rounding and, not having wrong results and all that stuff. And that opened the way for things like Java and other languages eventually, right? Because we cared about portability, we cared about performance, we cared about developer productivity, right? Now, fast forward from all of that to today. We went from a world where we only had to program one CPU, right, at a time from different vendors, albeit, but we had stable abstractions. And now we're in a world where we're saying, I have to program a single GPU. That GPU could come from any different vendor. Each vendor has their own particularities or different messiness in their stack that you have to go and navigate. I have to think about different number systems.
Yeah.
They're not standardized anymore. Everyone implements them differently. Then there's other companies building chips that have look nothing like a GPU, right? And that completely changes things.
Yeah.
Developers are not used to thinking about things that don't have flat address spaces, right? You think about distributed memory and all the complications it brings. You think of NUMA, and now you have to take all of that into account. And then that's still within one vendor's domain, right? You can get a whole multitude of options from any of the vendors today. You'll have different CPUs, different GPUs, different interconnects, different racks, different chassis.
Yeah.
Everything changes with that.
Yeah.
And we need to be moving faster than ever before.
Yeah.
So we need a stable abstraction that allows us to make sense of all of this at every scale, in every topology it can exist, and give developers productivity back. Because otherwise we can't progress fast enough, right? And that's the role compilers have to start playing again, right? So the view was kernels have now become the new assembly, right? Now, if people are hacking kernels and trying to find inline PTX and doing all these other types of things, that tells me, yeah, they think the abstraction's broken,
Yeah.
right? And there's so much complexity that exists that they can't navigate it. So if you can raise the abstraction, give them a programming model, they can express their thoughts cleanly and find a way to give them performance on all the different variations underneath. Like, isn't that just a better life?
So we're talking about the complete demise of the kernel at this point. Can we get rid of it completely? I feel like it's kind of central to the way we think about programming AI architectures right now.
I think it is central, but it's for a legacy reason, not because it's the correct answer, right? I
Okay.
think it was the correct answer for its time,
Yeah.
right? And at that point in time, we were still programming single GPUs,
Yeah.
right? We went from, how do we manipulate pixels and triangles to do certain things? And then that abstraction allowed to carry forward into what became CUDA. Right? I think the original nomenclature was UDA and then it became CUDA. But CUDA itself has sort of been evolving along the way. Right? It went from being a DSL to an entire ecosystem of libraries that were fully optimized and available for you to go haul into and do things. Then you had other things bolted on inside of it for being able to scale out and do other stuff. But that's still within one vendor. We're going into a world where every single compute from every vendor that will be produced will be plugged in and is something a developer will want to target. The demand for AI is that intense. Any piece of hardware is going to be used. A100s are coming back online because that demand is so intense,
Yeah.
right? There's a world where MI300s start becoming something people want,
Yeah.
right? There's people will bring triniums like previous generations online because they have them, right? And someone will get to figure out how to target them,
Yeah.
right? So the world that we were expecting, and part of the reason we went into this was many different generations of chips from many different vendors and many topologies at varying scales with different interconnects will come online and someone will figure out how to target them. And there's not enough performance engineers in the world to go and write those kernels for every single variation of workload that we want to target.
This new trend for disaggregation, I feel like, is making the picture even more complicated when people are deliberately putting in decode acceleration and so on different hardware. I mean, it sounds like a really complicated problem. Do you think it's
Yeah.
getting more complicated as it's evolving?
I think there's a degree of complexity. I um, we're from like saying that we operate at the height of complexity for every single thing, right? I think this is no different. Disaggregated inference makes a lot of sense, right? The prefill part is very, very compute bound. The decodes are memory bound, right? So GPU like hoppers, they were built for basically like 295 flops per byte, and that's the rich point. Like
Yeah.
below that, you're communication bound. If you look at token generation in a transformer or an autoregressive transformer, that's about 3 bytes. Three operations per token moved or byte moved words. Um, that obviously means I'm not getting any utilization out of this thing. So trying to find a way to separate that and try to apply different kinds of techniques and batching it and do all these other things help. Right? That's the best way to brute force performance. Right? But ultimately the choice comes down to, do I refetch or do I recompute? Right? Those are most of the decisions you start making. And I think there's a greater possibility of ways of expressing compute for different hardware that we haven't tapped into. And this is where, compilers can be useful. If
Um,
I think about any piece of hardware, every single microarchitecture, the architect of this thing had envisioned a certain way the workload was going to be written. And if the workload is written in such a way, it will always be best in performance, at which point I cannot get more. So the performance comes from the reorganization of computation around the memory hierarchy, taking into account all the system's inefficiencies and what is good at and what is cheap and what's not, and thinking about the communication lower bound of that operation. Right? It doesn't make sense to go from reading from memory, doing certain operations, writing back to memory, going all the way to HBM, then refetching it all the way back from HBM because you need to do the next thing. A kernel's worldview is only the thing within the kernel itself. Like it has a wall around it. It doesn't know where data is, where it's coming from, what operation's coming next, or any of that stuff. So if it writes back to HBM, like that's the normal thing to do, right? And GPUs tend to use DRAM as the main memory. So that is just a default path. All the gains come from saying, I'm going to keep things in fast memory, which is nearby. And if I have operations that depend on that memory, I should just continue doing those operations, reusing the same memory as much as I can, because then I can do more for the same amount of data moved. And data movement is really, really expensive,
yeah.
right? On the single GPU, about 65% of like energy cost is just data movement. Right? 10 to 15 is the computation, right? Depending on the chip. So the entire kernel model was built for optimizing the 10 to 15%.
Yeah.
We're not solving the important problems,
Yeah.
right? I think it's time to start switching our thinking to how do we solve for programming at the system level and like raise the abstraction so developers are more productive, but they still get best in class performance. Right. And there have been many efforts at this throughout history. They all failed because they were trying to look at things in a very isolated view. What we went and thought was, we can't actually find a reason why this isn't possible. And we looked hard, we spoke to everybody around this. So if it isn't impossible, what does it take? Right? What are the pieces of ideas that are just floating out there that people haven't pieced together, and what's missing? And that was the work we started doing. And having come from being a hardware company, we had a lot of insights into the different kind of hardware and the architecture space and how things could go and the impact of all of this. So we got to answer a lot of those questions. And ultimately, that meant building a fully parallel graph optimizing compiler that is hardware parameterized, right? And that basically enables it to do things like partitioning, blocking, tiling, schedule generation, fusion, loop unrolling, and other things, thinking about different kinds of schedules, and then finding the best way of expressing this workload for that piece of hardware. So the execution model itself is hardware independent but parameterized, right? And that allows us to just reason about certain things that a compiler wouldn't normally be able to do, right? And then the obvious thing is there's thousands of operators out there, right? The operator mapping problem has been, fairly hard, and this is where graph compilers have fallen short. It's why we keep falling back to kernels. The thing that we realized was there is a basis set of computation that all of these operators map down to. So we made that our primitives, right? So all of these operators can map down to this, and now you have a very closed set that you can reason within, and that favors graph compilers.
I feel like over the years, people have tried to solve this in a number of different ways. And one of the current fads is, or not, I don't want to say fad, one of the current approaches is write a domain specific language for that hardware
Mhm.
or write a Python based abstraction. There are other approaches out there, but why do you think they're falling short, or why do you think your approach is the best?
I don't know if my approach is singularly the best. I think it is the best that I can come up with right now, and it's also
Okay.
right. Something better could come, and if I'm convinced that that thing is something we should try, we will try it. Right? I have a decent amount of humility around like this isn't perfect, but it's good enough to address a lot of the problems, and we'll learn more as we do things, and then we'll improve. In terms of DSLs, I think DSLs have played a very important role, especially if you think about AI. Like people aren't going to be okay. Actually, let's backstrap a bit. There is enough complexity for a researcher trying to come up with a new model that they shouldn't be trying to do everything from scratch. If you're trying to solve for productivity and you're trying to solve for a specific domain, and the domain is somewhat static, right? And in this case, it's just linear algebra,
Yeah.
right? If that is the case, why not write a domain-specific language, right? The abstractions are clear. The operations people are trying to string together are clear. You don't have to worry about things like reverse mode automatic differentiation and all the numerical analysis that goes into that, making it stable. Don't worry about number systems that much. I mean, researchers don't care about where performance comes from. They just want it, right? So the easier you make it for them, the better things are. The cost of exploration has gotten way too high right now. Ideas are, they either survive and win or die based on the hardware they're being written for. And if you are dependent on kernels to give you the performance in order for you to try an idea and go from a local device up to a larger run, eventually to a supercomputer run for a large pre-training type thing, and then going from pre-training to mid-training to post-training to test and compute scaling and RL environments and all agents and eventually and everything else that comes. Each one requires a mini army. to kind of get working, right? And there's different tools, and that slows the experimentation down and the ideas down. So you want to speed all of that up so that we can explore more of the possibility space of architectures that could exist. Like, I think transformers are great, right? But are they the best we could do? I think we could do better. But we have optimized so much into a certain direction that it is cheaper to continue down that path than try something new, right? So transformers have sort of become like this Nash equilibrium for the AI industry, right? But we've got more compute than we've ever had in history. It's getting cheaper, but everyone's mostly playing around with the same idea,
Yeah.
right? So if you have better tools, you open up exploration again, and more ideas can be tested quickly, and they
Yeah.
can be scaled up quickly.
Yeah.
And I think that's a better world, right? So domain-specific languages help in those kinds of places. And also, they hide a lot of the complexity, so you can focus on, your particular domain in which you are an expert, so you can get more leverage,
Yeah.
right? So I think they're not good.
Are we talking about throwing away much of the compiler infrastructure that we already have? Do you want to start from scratch, or can we kind of evolve into the approach that you're talking about?
I think every single evolution has a ceiling, right? There is the initial state at which you start sort of and the constraints you're in sort of predetermines where you can end up, right? It's sort of like the question that I think about a lot is like, when does better stop being better, right? If conditions start changing rapidly around you, right? What is good at one point in time becomes less good over time,
Yeah.
right? So the curve of improvements, as you think about them, like people talk about exponentials, but exponentials are made up of these many parabolas, right? So it's like goes up and then down, like you keep stacking them. So things will improve up to a point, and then there's an inflection point, and it starts getting a bit worse. Usually because it gets too expensive to continue improving. You squeezed out all the improvements that you could have. But there's another paradigm that has a promise to take you way further, but it's a bit worse right now. So if you jump onto that and then you ride that up, right, you get way more out of it. And you have to be able to leave the old thing behind to jump to the new thing to make progress. I think we're in one of those cases,
Okay.
right? The reason being, all compilers and all infrastructure has a path dependence all the way back to something like Algol 68, right? So the ideas that were there are still present today in how we think about compilers, and were built for a very particular view, and it's CPU centric. Where the world is moving towards accelerator centric with CPUs as a backbone for like orchestration and things. So it already tells you things have changed. And it isn't just even accelerator centric. We are programming supercomputers, and they have very different properties. Like, so we need to be compiling for the system, not for a device inside of the system and stitching it together. Right. And that requires thinking about infrastructure and, compilers and representations and transformations and runtimes all differently.
I mean, we talk about the system level. We spoke about complexity a couple of minutes ago, but is compiling for the system level, like with system level awareness, really a tractable problem? Is this even achievable? Is my first thought.
It is. There's been a lot of different efforts. If you like, Cray has been working on this for decades. Right? If you go back to the old days, like they were thinking about these things. All the different people in the supercomputer and HPC world have been thinking about these problems for a very long time. There's a lot of prior literature that tells us that it is a tractable problem. There's always been a few missing pieces. Right? If you don't have enough information, right, you cannot reason about things. Right? For example, compilers tend to throw away information. Right? Once things come into the compiler, you have thrown away information. And this is where the whole parallelizing compiler came from, is trying to recover the information it threw away,
Okay.
right? And then try to infer parallelism from there. That is a very hard problem. Well, if you don't throw away that information, everything is by default parallel. So you have an easier time and you don't have to recover it. Now you can do different kinds of optimizations,
Yeah.
right? Thinking about the distribution side, if you have a good cost model of the amount of bandwidth you have and the amount of memory you have, you can think a lot about, this is the most I can put into a device. that is the level at which I partition, right? And now I need to go lower than that and think about what is the optimal partitioning at these different levels. And if I have these schedules built around this, right, that is the best I could ever do. So you have to think about, I have a very, very large search space. How do I prune it down to make it tractable? Right. And there's known good choices. Like we've learned a lot about how do we make high performance computers go really, really fast for different workloads. So there's a lot of stuff there that we don't have to go and recreate or rediscover. Like we can be smart about this. Right. And that's the entire point of engineering, is solving really hard, interesting problems and making them tractable. And then there's the entire thing. I was like, it's a high dimensional space. So clearly this is an AI problem. Neural networks are good at high dimensional spaces. If you think about compilers and most of computer science, they're intertwined with the history of AI. Everything was AI until it became obvious, right?
Okay.
And compilers are a form of an expert system, which is, one class of AI from the days of yore, right? People did things, they understood the hardware really well, they understood the computation, all the different transformations that resulted in performance and correctness. Compilers were designed as, basically as verifiers. So you could generate candidates and test them and then produce things, right? But it's expert knowledge that's always baked in. Right? So they are kind of like an AI, and that opens up, if you've structured things correctly, that opens up a possibility of bringing more things into it over time. But you need to have the right foundation for doing that.
So how much of this have you actually built so far? So I've been following Lemurian obviously over the last few years, but I know you were a hardware company originally. You've changed focus to the compiler infrastructure, but how much of that have you actually built? What stage are we at
Yeah.
right now?
As you can imagine, building something like this is not easy. When we met, I didn't have gray hair. Now I have at least a couple 10,000.
Yeah, me too.
Well, yours works better than mine does right now.
Thank
Mine's
you.
an absolute mess. The We had to go and read all the prior literature, understand everything that has been tried, when it worked, when it didn't, what was true at the time, what's changed, right? There's is conflict that exists between, having an adaptive runtime that can do a lot of things versus the kernel model. One wants dynamicity, the other wants static, right? And if you have over optimized in one case, you've limited the other, right? And if the thing is data movements, then you want to be a bit more runtime centric and less kernel centric, because that just gets in the way. Right. But if you're doing all these other things, then that was sort of the realization that the thing that has held back all these other ideas is the fact that we kept falling back to kernels and no one fully committed to the post kernel world. Well, I think this is an important enough problem that requires a serious effort. And in order to make it a serious effort, you have to do it as a company. It can't be done as research, because as research, you're thinking about, how do I get something 70% ish complete and then publish a paper on it and then move on to the next thing. Right. But the most important work is the last 30%.
Yep.
Right. And that requires a very dedicated effort, right? And that's why we dropped doing the hardware. A company can only do one thing well at a time. I can't build good hardware and think about base system and think about this compiler and everything else that goes along it within the library and the DSL side, and try to get this in, foresee this into the ecosystem. And you have to think about stable abstractions as you change things in hardware as well to make the programming model easier. So in this case, we had to go rebuild all the infrastructure to build the tooling, to build and test the compiler, bring it up on hardware, work with the hardware vendors to characterize the hardware to make it something that is representable in the compiler so it can reason about this and is making good choices. Right? We didn't have the benefit of saying there's existing infrastructure out there. Let's just use that and bootstrap it and just make it work. This is an entirely new way of thinking about the problem. But the good part is we have figured out what it looks like.
Okay.
And it works end to end right now. It's simple cases, but the way it works with compilers is the moment you have something working end to end, you're about 90% complete. From here, it is getting more coverage, making sure the choices we're making are generalizable, things are porting to new systems properly. We're getting coverage over different models. Performance is coming. It is the way you expect it to. Like make performance the default path, not the path you have to opt into as a secondary thing and do additional work to get. And then how much performance are we getting out of the system by default? Like, so if we get things like jagged performance because we didn't characterize something well, is that a limitation of the compiler in the runtime, or is it something that the user needs to intervene in? And where does that live? Like, what is the user experience we want to create around this? What tooling do we need in order to make it more usable and friendly for a user? Right. But when I think about how to make this in the product, then it is, I want this to feel obvious that this is the way we should have been programming all along the moment you touch the system, right? It is simultaneously a painkiller and that you don't have to deal with infrastructure. It doesn't hold you back. It enables you now. And it's a superpower because you can now try out new ideas faster than you ever thought before and get them into market, right? So that requires getting a lot of things right? And that requires being very, very disciplined and on how we're building it, what we're building. And for us, it's correctness first, performance second.
So you're working with NVIDIA and AMD. You're starting with GPU hardware right now. How far along are you with supporting those GPUs? And do you have plans to add something more novel and exciting from the world that I come from?
Yeah. Right now, GPUs are the focus until the end of the year. We are in conversations with every single chip vendor that's building interesting hardware that can be compiled for.
Excellent.
Um, there are some people that have built hardware that looks really, really cool, but it's just great hardware that the compiler cannot target. Um, like that ends up being the case more often than one might expect.
Really? Okay. Or maybe tell me later who those people are, because yeah, I'm very curious. Okay.
Yeah. Next year, we will be launching with a few non-GPU hardware.
So there's quite a lot of excitement right now about using AI to generate code, generate kernels, even help build compilers, even do the work of a compiler in some cases. What's your take on that trend? Are you using a LLM or AI somehow in your stack, or how do you use AI for
Yeah.
for what you want to build?
We use it to help us find new ideas and test out new ideas rapidly,
Okay.
but we haven't been able to use it that much internally because we're building everything from scratch. There's no outside dependencies in our stack. Everything's built in house.
Okay.
Right. So that makes it somewhat harder. And we went and invented a whole lot of new techniques and ideas to make a lot of these things tractable. And, when we start using a lot of the coding tools, they're good for a little bit and then they lose coherency after a couple of steps. And that makes it hard and diminishes productivity for a lot of the team. So we're using it differently than most other teams are right now. I think that's just the curse of space we're in. The only moat, as I say, is the things that are just really, really hard and just outside of the capabilities of AI. Um, in terms of using tools to generate a lot of the kernels and make that part of the solved problem or use it as a compiler, I think the LLM generated kernels with verification, they help, but they only help on one aspect of the problem, which is I need kernels, right? And then you can verify them, but the verification only tells you if the thing you generate is correct. The performance thing is a separate thing,
Yeah.
and you have to have good baselines to compare against. And you need to know what is the right set of instructions, like to call into, what does data movement look like? Where is that happening? How do you control it and organize it? Like, and that's a very, very different problem. Figuring out what parts to fuse either on the tail or on the head or both, or how do you want to partition things? All of that comes into play. And that's a very large space to reason about. And I think they can help on part of it. And that is useful. But the more important part is, how do I generate communication optimal kernels that scale not locally on one part of the computation, but the entire workload? Because there are many cases where you can have a super fast kernel, but you haven't really moved the needle in the workload, right?
Yeah.
So our job isn't to give you fast kernels, it is to accelerate the workload,
Yeah.
right? And that's why we took this particular approach instead of saying we want to build kernels. Because if that was the answer, and that was one of the things we did explore, And we explored a lot of really wacky ideas internally before we settled on this. Like really, really goofy sci-fi comedic type of ideas internally, before we decided like, yep, that's not a viable path. We they can help in one part, but there's enough latent performance in these chips that we cannot access if we continue down this path. Right. And if demand is growing so aggressively that every single company serving these tools has latent demand that they can't serve because hardware is underutilized, even after writing these best kernels, clearly the problem is different. So if these hardware have 2 to 3x capability inside of them, and we have, $500 billion of hardware build out, there's about another 500 to $1.5 billion, $1.5 trillion of, value that is just sitting there that is untapped. How do we go unlock that?
Yeah.
And that is a very different question to ask than what the kernel model asks.
Yeah.
Right. So I think they'll help. There's special cases where it'll help. I think if you are a regular model, like a very, very monolithic kind of model, and you're small enough to fit inside of a single GPU, the kernel paradigm is amazing. If you go towards more complex hardware and you are thinking about multi-device or multi-node or multi rack and multi-cluster and all that kind of stuff, kernels will not have to come and save you.
Ultimately, in your vision of the future, if AI workloads become kind of hardware agnostic and you can compile for the system level, so it's make it much, much easier to change hardware, have disaggregated inference, we talked about heterogeneity, all these things that are adding complexity. If we make all that easy, does this change who wins when it comes to AI infrastructure? Does it change who wins for chips in particular?
Yeah, it's interesting. So, well, firstly, I don't think we make it easy. I think we make it dramatically easier. There's always going to be a
Easier.
little bit of hard. Like, there's
Okay.
always going to be a little bit of hard. Like, this is like magic compiler thing doesn't exist.
Okay.
Right? There's a compiler that can be sufficiently smart, it can do things. Like, and magic is just a word we use for something we don't fully understand yet. Right? Right. And Arthur C. Clarke used to say, like, any sufficiently advanced technology is indistinguishable from magic. Right. So
Perfect. Yeah.
when people say it's a magic thing, it can't work, it's mostly because they haven't understood how it can't work. Right. So it's just surprising and feels magical. And that's actually a great product experience to go for. It means we've done our jobs well. Now, the there's an interesting assumption that you're making in there that hardware is fungible or commoditizable. Every hardware is built differently, different microarchitectures, different memory hierarchies. Every single topology in the system is going to work better for some things than for others, right? If you go to different clouds, they have set up things differently. They have different capacity. They have different networking. They have different memory. They have a lot of other different types of things that they've optimized for. So certain workloads are always just going to be better in certain places. You have to be able to pick the best one for you, right? And if you can't pick the best one for you, there's a second and third best option as well available as well, right? And that is what opens up. Today, you are locked into one place of doing things, right? So if you have written and trained your model using some flash attention kernel, for example, that is locked to one piece of NVIDIA hardware because flash attention isn't portable. There's different implementations on different architectures, right? But if you have written the attention operator higher level, like in the DSL, we can recreate versions of flash attention that are optimized for different hardware, right? So you get the correct result by writing the high level thing. And now you've gotten performance on these systems. But you will get the best performance on those systems. Portable performance doesn't exist because performance isn't the same on every hardware. Right? It requires different things. So that sort of makes hardware not commoditizable, but it makes it more accessible and makes more ideas accessible faster. Right. And the economics will change in terms of who can do things. Right. But hardware availability is still going to be an advantage. Right. I think the average researcher who could not try an idea because they didn't have an army of people working with them to help them try their ideas, that will go away. I think the age of research will be unlocked by this. I think larger scale deployments at better economics will be unlocked by this, which will open up more applications and new ways of using things. Right. And like personally, like part of the personal incentives I have around this is I think the worst possible future I can imagine is when AI progress essentially stops because nobody else can manage to train a more complex model, right? But better algorithms, again, there's more performance coming from algorithms than there are from hardware. So if you have better algorithms, which can allow you to express new ideas, and those ideas end up being more sample efficient, so you can leverage more of the data in more interesting ways, and they are more compute optimal, that is essentially a massive advance. I don't need to build as big of a computer in order to realize that. I want those ideas tried out because I do believe they exist, but they're just not something we can go after for various economic reasons. I think that becomes possible. Right? If it's only landlocked to certain areas, right, or certain companies, then those values get propagated, and like the way people think gets dictated by that. I want more innovation. I think it's still early days. Right? And if this is the best we can do, then I think that's one of the worst futures that we end up in.
An exciting vision for the future there, Jay. Thank you so much. What a wonderful
Of course.
conversation.
Thank you for letting me ramble.
Thank you so much, Jay. Plenty to think about there. This episode of AI with Sally was brought to you by Lemurian Labs, and thank you so much, Lemurian, for sponsoring us. If you want to learn more about Lemurian or hear my previous episode with Jay, please check the links on the podcast page at eetimes.com.